So we have a matrix for the discrete Fourier transform, right? But we need to analyze each row of this pattern, okay? In the geometrical relation between the Euler identity and the input signals, right? And so the node 1 can be written as just like this one, row 1. For the row 1, we have the 1, 1, 1 and 1 signal, right? And so we need to draw the Euler identity, im and real, right? And so what's the meaning of this row 1 value in here? 1, 1, 1, 1. And so we have the 1, I, minus 1 and minus I, right? And so I can say that at each case we have the 1 turn value, right? At each case 1, 1, 1, 1 in here. Okay, what about the row 2? For the row 2, 1, I, minus 1, minus I, right? And so I can draw the another Euler identity in here just like this one. And so in this case we have the what? 1, I, minus 1 and minus I. And so what's the pattern of this term? 1, 1, 1, 1, right? We have the 4 pattern in here, right? And so the row 3 can be given with the what? 1, minus 1, 1 and minus 1, right? And so we have the signal in here. And so what's the pattern of this term? 1, 1, right? 1, minus 1, 1, minus 1 in the geometrical relation. And so in the row 4 we have 1, minus I, minus 1 and I, right? And so what's the geometrical relation for this pattern in here? This 1, this I, this minus 1 and minus I. And so 1, 2, minus I, right? And so we have the what? Minus 1, right? It's the pattern. Okay, and so this is the 0 around pattern, but with the based on the what? 2 pi. And so this is the 2 pi minus pi 2 around, right? This is what? 2 pi around, right? Or 2 pi minus 3p 2 around. No. No. Because we can turn at the counterclockwise or the clockwise, right? And so we can use this formation or this formation in here, okay? And so at each around, just see that we have the 360 degree, right? What's the degree of this? 270, right? What's the degrees of this? What's the degrees of this? Okay, and so if we have the 4 pattern, we can analyze this signal at this rate of the degrees. Okay, and so at each pattern, if we have the returning point values in here, just like this one. Suppose that we have a sinus value, pi, 2 pi. We have the period of the 2 pi. And so we can say that this is the 1 hertz, right? And so we can analyze this signal based on this information. And so right now, you can understand that what's the meaning of this pattern in here, right? At each step, 360 degree deflection on this pattern. And this one, 270. This one, 180. This one, 900 degree. And so we can return to the same point of this pattern in here, just like this one. Okay? This is, we can create the row and each column values of these terms. You can understand that how can be obtained the frequency pattern using the Euler identity in here. Do you get it? The notion of these terms? If you multiply these terms in here and then 1, 1, 1, 1, and so at each time we can around the 2 pi deflection in here. Okay? And so in the 2 pi we have the 1 hertz signal, right? This is the base or unity frequency pattern for the Euler identity. Just remember the Fourier transform proof, right? And so we can analyze it. You get it? These angles, for example, we have the one value in the first step, but in the second step we have another one value, right? This is related to x n equals 0. This is the x n equals 1, right? First measurement, second measurement. And each measurement can be collected or multiplied with the column of the input matrix X. And so 1, x0, 1, x1, 1, x2, 1, x3. This is the multiplication. And so at each case, we need to give the frequency pattern to these times, right? And so in this case, we evaluate our signal in the with the 1 hertz signal. But in the second step, just see that. What's the values of these terms? Yes, but we have the 270 degrees, which means that 4 divided by 3 frequency is applied on this signal, and the selective pattern returns to the frequency magnitude in here. And so we have always a greater value in here, just like this one. And so we can say that this signal has the 1 hertz frequency, right? This is the general pattern, because at each case we have the 90 degrees in here, 0 degrees in here, and so we have the 100 degree, and so we have this degree, right? And so this is the 1 hertz. What's the meaning of this one? What's the values of this thing? This may be the 2 hertz, or the 4 hertz, or this is the 2 hertz. This is the 4 divided by 3 hertz in here. Okay? And so we can scale to to hold the pattern based on this information, just like the continuous Fourier transform, right? And so each shape has the specific frequencies in here. If this is the 1 hertz, and so this is the 4 hertz, this is the 2 hertz, this is the 4 divided by 3 hertz, right? Okay? Okay. And so, what about the property of these terms? Just remember that analyzing each row gives us to W 1 1 1 1, right? So 1 1 1, right? And so I minus 1 minus I, right? And so minus 1 1 and minus 1, right? And minus I minus 1 and I, right? See that this is the first pattern of the signal. Okay, this is the unity based signal. This returns to what? The summation of the values of these terms. Okay, and also this is returns the first value of input signal, right? This is the base for your transformation. But see that what's the summation of this term? Okay, what's the summation of this term? 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 And this term? 0. Is this a coincidence? Huh? What's the meaning of this? At each row and column gives us to what? To 0. Which means that V returns to the what? To the same point at each frequency characteristics, right? And so, if we have the 8 Hz signal, and then we can analyze the signal without losing energy of the time signal based on these matrices, right? You get it? If we multiply the any signal x1, x0, x2 in here, these rows multiplied with the what? With the whole values of the x. Just remember that. x0, x1, x2, and xn, right? And so rows multiplied with this one. And so each row with the coefficients of this term, this matrix does not increase or decrease the values of these terms. Just scale to the what? To the values of the x1, x2, and x3, right? Just see that. If you have the any signal in here, just like this one, for example, this is the 1 seconds at this point, right? And so what's the frequency of this term? 1 Hz, right? 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 Okay. See that. What's the values of this term? Pi divided by 2. What's the values of this term? Pi, right? What's the values of 3 pi 2? What's the values of this term? 2 pi, right? Okay. And so if we have the signal pi 2, pi, and this one, right? This is the 1, this is the 0, this is the minus 1. See? And so, if we multiply these results, 1, 0, 1, 0, 1, 0, right? And so are the matrices given us to the what? 0. And after that, 1. And after that, 0. And after that, minus 1, right? And each step, if we multiply this one, this one, this one, the first row multiplied with these things generates to the what? To the 0 value, right? Because the first row, 1, 1, 1, 1, 1. Okay. And so in the second row, 1 times 0, 0. And this is the I, right? Minus 1, I. And so minus I times minus 1 gives us 2i, right? Is correct? Okay. And so in the second case, 1, 0, minus 1, 1, minus 1, 0, right? And so 0 and minus I minus I, and so we have this value, 2i and 2i, right? And what does tell us right now? This is the sinus signal. For example, if we are using the unity signal, we can calculate it. This is the watt unity signal, 11114, right? Right? 111. This returns to the what? 0. 0 and 0. What does tell us?
Summation of the signal to that point is 4. For the first one, since it is 2i, so we have like 90 degree increasing. Describe the characteristic motion of the signal.
Yes, but see that the DFT matrix produced for the unit step signal has the 1 value, which relates to what? 0 Hertz, right? But the other one gives us to what? This one. I think this signal produces these values, but this signal, this one, produce the 4, but we need to normalize this form because we have the 4 value in here, and so I divided by 2, I divided by 2, and so this is the divided by 4, and so this returns to the what? The 0 Hertz signals in here. Using the what? Using to this domain. But in the real life, we only deal with the what? With the absolute value, because we cannot see the imaginary part of these signals, right? And so in the magnitude domain, we have the correct values of these terms. Square form. And so this is minus 2 divided by 2 in the square form, and so if we have this signal, and then we can say that we have a periodical signal in here, just like this one, for the 4 values of these terms. Okay, we can scale the what? The fs may be 500 Hertz, and then we can say that we have the 1 second value in here, just like this one. Okay, do you understand the meaning of the row values in here? Just like this one, each row creates the what at summation gives us the 0, unless to the what we have the periodic signal, right? We can extract the information for the periodic signal in here, just like this one. Okay, in the MATLAB application, you will see that in the fast Fourier transform or the Fourier transform, discrete Fourier transform gives us to what? The specific pattern of these signals. If we have this signal and then we have the specific values of these terms, and so we can analyze the whole signal in the absolute domain, and so we can put to the what? To this signal. We have the magnitude in here, the absolute form of the signal, and so we have the specific points of this one for the 4 points. Okay, we return to the what? returning to the same position in here. You will understand that, these concepts. But this is the basic definition of the discrete Fourier transform. If we have the periodic signal in here, just like this one, and so we can have the values except from the what? The 0. Okay? Baran? You get the notion? Okay. And so, what about the properties of this matrix? Firstly, this matrix W is unitary, which means that orthonormal. What is the meaning of this? The inverse value of this matrix is equals to the what? The transpose of that. Okay? Which means that transform W times W equals to W transform, which is equals to the what? The I. Okay? The inverse is equals to the what? Each other, but in the complex conjugate form. Okay? Otherwise, we cannot get the what? The summation of the each row and column is equals to 0, right? We cannot do that. We cannot get that. Okay? The other important property is that is the symmetry, which means that WT is equals to the W, or this matrix, the transpose of this matrix equals to the what? The transpose of that, the itself. Okay, W transpose is equal to the W. Okay. In the third property, the circulant form, which means that we have the matrix in here, just like this one, 1, 1, 1, 1, and 1 I minus 1 minus I, and 1 minus 1, 1 minus 1, and 1 minus I minus 1 I. Okay? In the circulant form, we can go to the right direction. We set order 1, 2, 3, 4. This one is going to up to this one, or the right direction, moving in here, and so does not change the anything of this one in here. Okay? This is the circulant property, which is the source of the frequency pattern of these terms. Okay? And also we can say that we have the sparse property. Sparse factorization can be applied in here, because if we have the symmetry and the unitary property, we can create these matrices based on the what? The many zeros, or the many factorization techniques. For example, just remember that we have the L transpose D elimination, or the matrix transformation in the what? In the linear algebra. We can easily apply this transform into this matrix, because each row and column values are the what? Summation of these terms are equal to 0, right? This is why we can apply this signal. But how we can show this property with the basis of the what? Examples. We can draw the what? This pattern, and also can draw the Euler identity. Okay? And so, if we have the 4 points, we divide this Euler identity to the what? The 4, which means that we have the 90-degree deflection in this area. But if we have 8 points, yes, and so right? And also say that this is the I, this is the 1, this is the minus I, this is the minus 1. Okay? So, what's the values of this thing? No. The magnitude of these terms, the hypotenuse, is equal to what? The 1 in the absolute form. What's the values of this term? Yes. 1 divided by square root 2 and 1 divided by square root 2i, right? This is the coordinates of these terms. And so 1 divided by square root 2 and 1 divided by square root 2i, right? What's the values of these terms? Minus I, right? And so what's the values of this term? 1 divided by square root 2 minus 1 divided by square root 2i, right? So we can evaluate the 8 points in this DFT matrix, right? If we have the 100 data, and so what's the values of these terms, or what's the angle, splitting angle? Just tell me. Yes. If we have the 600, if we have the 360 value, and so we should split this area into the what? 1 degrees. And so we can create the what? Our matrices in here. Okay? So just see that. This is the regional inference property. So we can build the what W matrix in here, just like this one. For always video, what's the dimension of this W, Baran? Huh? What's the dimension of this matrix? Yes, n sharp n, but the n times n, what's the values of the n? 8, right? 8 times 8. Okay. And so we have the one pattern here. This is the first one. It's the second one. Third one. Fifth one. 1, 2, 3, 4, 5, 6. And so we need to add one another, right? We have the 8th row in here, just like this one. And so if we return this point at this direction, we can say that this is the 1. If we return this direction 2. Okay? If we are going to this direction, and so in the first place we should say that we have the 36 degree, 360 degree. And so what's the values of these things, Baran? Just tell me. 1, and so 1, 1, 1, right? This is the what? This is the direction 1. In the direction 2, we have in here 0 degree, right? It must be 0 degree, right? Okay. In the second case, what is the values of the degree in here? Yes, 315 degree, right? And so, what's the first value? 1. What's the second value? No. Yes. Yes, and yes. What's the values of this thing? What is the values of this thing? No, there is no comma. No. What's this thing? Gives the coordinates of these terms. In the one direction, we have this one, right? And so this terms into the what equals to 1 divided by square root 2 minus 1, 2. Right? Yes. This is the what? This is the 315 values. Okay? We can, because we can coordinate these terms into this one, in the one domain. Because in each domain, just see that we have the one value, but this is the absolute value. If we take the absolute values of this term, we can take these coordinates. Just remember that this plane is only giving to what its absolute values of the term. Okay? Just see that this is the I, right? But the absolute values is equals to the I. Okay? And so, in the second place, what is the third term of these matrices? You are sure about that? Okay. I just test you. Minus E. And after all, what's the final values of this term?
1 over 1 bölü 2
Mm-hmm.
artı 1 bölü 2 pi.
Yeah. Okay. And so this is the 45 degree. Otherwise, we can circulate these times or these times. Okay? This is the property of the what? Circulant region property. We can search in the one direction or the second direction. Right? Okay. And so, what's the values of these terms? What's the values of these terms? Okay. And so, what's the last values of these terms?
1 bölü 2 eksi artı 1 bölü 2 i.
Yes, I. What's the first value? What's the first value? 1. And what's the second value? What's the second value? Minus I. And it goes on, just like that. And so, do you understand how can we complete or fill the DFT matrix based on the what? Euler identity. Do you understand that? Do you understand the everything? Okay. And so, this is the complex process to calculate the DFT matrices, but in the MATLAB application, I will show that this property. Okay? Because in the two direction we have this one. In the one direction, this the what? 1. If we have either goes to what? The 270 degree in the two direction, or we have the 90 degree in the one direction. just going to what? The 90 degree is equals to I. Or just going to this way, 270. It goes to what? To I. Okay? This is the second property. Okay? In the first place, it's the 1. Okay? This is the 1. Right? And so we have the what? 270 degree. And so I can go to the 270 degree. What's the values of this term? Okay? Just get it. And after that, yes, this is the 100 and this is the 1. What's the values of this term? Minus 1, right? This is the graphical representation of these terms, okay? Any question? Yes. Yes, we divide the whole region to the what? To the 8. We cannot build the infinite impulse signal because this is equal to the what? Continuous Fourier transform, not the discrete one. In the discrete system, we have always a limit to sampling the ratio based on what? The Nyquist criteria, right? Okay? Yes. This is the what? This is our circulant matrix to build your DFT signal. In the examples, we can apply the Fourier transform, discrete Fourier transform to the what? To the whole data. And then, for example, if you have the 1000 data, we have the 1000 times 1000 coefficients. Which means that if this is the values of these terms, and so we can slice the whole circle into the what? The 1000 points. And what? This is the what? The circulant or the Euler formulation. And then we know that if we take this sample with the basic frequency rate, for example, 1000 Hertz, and then this signal interpreted with the what? The 500 Hertz values of these terms, right? Because the Nyquist told us this feature. And then, just remember that if we have the n data, but we can normalize with the what? With this data. And so, this pattern gives us to what? To scale to what? The 0 to fs divided by 2 frequency range, right? And so, if we change the sampling rate in here, we do not affect this one because this circle gives us the unitary property or the normalization form of your frequency pattern in your signal, just like this one, right? In this case, we have always this circular pattern in here. Up to now, if we increase the values of these terms, we may have the 2i and 0 and 2i value in here, right? In the what? In the second order system in here, okay? See? Simple. And so we have one more topics about the fast Fourier transform, but I will show this Fourier transform in the what? In the not next week, in the before the MATLAB session. I will produce or the prepare the MATLAB session of these algorithms in the what? The fast Fourier transform algorithm in the MATLAB application, DFT application, FFT application, and then you can visualize the whole things based on the what? Based on the studied is examined in this lesson. Okay.